who are watching on the live stream on YouTube, and also give people a couple more minutes to join the meeting. So later on, we'll also be having a question and answer session on slido.com. So if you head over to slido.com and put in the event code #EEVM, that will take you to the question and answer page, which we'll be using for sharing questions. This is to accommodate people who are also watching on the live stream in YouTube, because they won't be able to post their questions in the chat like those of you here in Zoom. So thank you again for taking note of that. That's just slido.com and #EEVM. I will show this again later. So if you don't catch it now, you can also hang on till towards the end of the presentation. So this talk will be shared later on YouTube. We now have a channel to share all the past presentations from our wonderful guest speakers. So I encourage you to head on down to this bit.ly here, bit.ly/EEVM-YouTube, and you can see all the past presentations on the Earth Engine virtual meetup. And feel free to contact the authors as well if they've shared their contact information if you have any questions about their talks. So up until the end of this year, we have our meetups happening once every 2 weeks. So this one that you're listening to now is Series A, and Series B is hosted by the Yale Center for Earth Observation and TC. TC, would you like to introduce yourself and talk a bit about what's coming up next for Series B?
Hello, everyone. I'm TC. I'm a PhD candidate at Yale University. And so for Series B next, I think a couple of weeks from now, we have a presentation about RGEE, because we had a lot of interest in GE map. So that's like the Python implementation of Earth Engine. So there is one for R, so for users who use R. So that should be very interesting. I will send out the link for that and the information for that in a maybe a week.
Yeah, and if you're on Twitter, you can check out the #Earth Engine Virtual Meetup, because that's where we've been posting a lot of our updates, as well as links to presentation slides and the videos. So if you're on Twitter, please look us up as well. So we are really excited today to have Professor Koreen Millard from Carleton University, who will be talking about geomatics in support of Canada's National Greenhouse Gas Inventory and the Air Pollutant Inventory. And this will be a recorded talk, but she's live with us here, and she'll be able to answer questions during our Q&A session afterwards. And if we have a bit more time, we always have a little bit of space for troubleshooting tips and tricks. So think about your questions now. If you have anything that you're working on that you're stuck on, or you have found this cool resource you want to share with other people, please feel free to share this later on during our tips and tricks session. So thank you and welcome again to Koreen, who's also here on the call. I'm going to go ahead and play the recording that she has sent to us. So here's the talk.
Hi, everybody. Thanks for coming to listen to me talk at the Earth Engine virtual meetup. My name is Koreen Millard, and I'm an assistant professor at Carleton University in Ottawa, Canada. I'm going to talk today about some work that started when I was a research scientist at Environment and Climate Change Canada. I'm going to talk about geomatics in support of the National Inventory Report and Air Pollutant Inventory Report, so using remote sensing to estimate emissions. I'm going to talk about why we need emissions inventories, how do they work, how are emissions actually estimated for these inventories, and then I'm going to give examples of 2 projects that I'm working on related to air quality and greenhouse gases. So why do we need emissions inventories? Well, we know that global warming is occurring and it is related to anthropogenic emissions. So national inventories enable each country to tabulate their own greenhouse gas emissions. And then internationally, we can bring this information together and assess how we're doing collectively, but also look at individual efforts and see where we need to improve. So greenhouse gas emissions are aimed at helping us reduce our anthropogenic emissions over time. In Canada, this is done through the National Inventory Report, and this is reported to the United Nations Framework Convention on Climate Change. And we use a method that's standard internationally. The IPCC has guidelines that tell us how we should produce these emissions estimates. But in general, what we're trying to do is get one number nationally per year, per emission category, and per source category. So for energy, and even within energy, there'll be subcategories. We need to know how much CO2 is emitted per year nationally, so across Canada, one number. We do this for both sinks and sources, and then report that to the UNFCCC. We also have an inventory report, or the APEI, and this is not reported to the same conventions, but we use the IPCC guidelines as well. And how we actually do that is using a very simple equation. We take the activity rate and we multiply it by the emissions factor to get our emission. And so what this means, I'll use the example for transportation. The activity rate is how much we've driven cars in Canada in a single year. So we've driven so many millions of kilometers in that year. The emissions factor would be dependent on your car. So I may have driven my Toyota Yaris 20,000 kilometers, but somebody may have driven a Toyota Tacoma 50,000 kilometers. And the activity rate is the number of kilometers, but the emissions factor depends on the type of car, because a Yaris presumably pollutes a lot less than a Tacoma. And so within the IPCC guidelines, there's 3 tiers of ways that we can use this equation, and the way that we can give data to this equation. The tier 3, which is sort of the gold standard, it's the highest level, the most complicated method, is a spatially explicit wall-to-wall mapping. And so that's where remote sensing, and that's where Google Earth Engine comes in. So when I was hired, I was told we really want to improve our emissions estimates using this tier 3 standard. How can we do that? Here's a couple examples of emissions that we need to improve. And one of them was mine tailings. So mine tailings, this is the stuff that comes out of a mine that's not being produced and not turned into ore. It could be in a pile, or it could also be in a pond. And so there were a couple assumptions being used in how we got this estimate of particulate matter, so total particulate matter emission. And the first was that the bigger the pile, the more emissions. So if you have a tailings pile and it's really large, you'll have more particulate matter emissions than a small pile. But there's also a relationship between the size of the pile and the mine area. And that's important because we didn't know how many piles there were. We didn't know how big they were. But we had estimates or ideas of how big mine surface areas were in Canada every year. However, what I learned is that that number for mine surface area was actually not very certain. And it was being calculated based on some old data that had a lot of assumptions in it. And so we were using a report that was created by Murray et al. In 1977, and they mapped 80 of the largest mines in Canada using Landsat 1. And then we were using a growth factor to extrapolate that size per year. And so not only did we not really capture all of the mines in Canada with this Murray 1977 report, but we also didn't really understand where the growth factor was coming from, because we had purchased this number from a private company, and we're just extrapolating on that every year. And so we wanted to improve the estimate of surface area of mines in order to improve our estimate of air quality from mine tailings piles. And the way to do that in my mind was to use wall-to-wall mapping. And what I first looked at was using Landsat, because we needed to go back to 1990. So Landsat's basically the only sensor that we can do that with. And I estimated that we need 1,285 Landsat images per year to map all of Canada. And that's not a super large number, but it was larger than we were able to handle with the infrastructure that we had. So we needed to use some sort of cloud system, and that's when I started really getting into using Google Earth Engine. So the way that we decided to map these mine extents was to build cloud-free vestibular pixel mosaics around benchmark years. So looking back at 1990, we built a benchmark year for 1990, 2000, 2010, and we did this with Landsat 5, building a bunch of different indices or indexes like NDVI, and using it to EM as well. In 2018, and looking forward, we're actually going to use a different method, and we tested this as well, using Sentinel 1, which includes the SAR, Sentinel 1 VV, and Sentinel 2, as well as Landsat and a digital elevation model. And in both cases, what we did was we used a classification approach. And we used random forest because it's built into the JavaScript API of Google Earth Engine. And we did something that is called transfer learning. So we extracted training data for the year 2000. And we did this because we had a database of mine locations around that time. But it wasn't a super certain database either. We had locations in there that were the mine headquarters instead of the actual mine itself. So we had to go through and clean those up and then collect even more training data points throughout Canada for mines, but also areas that were not mines. So in total for the year 2000, we had about 12,000 training data points. And we created a random forest model for that year and predicted on the data from the year 2000 and produced maps of mine area like you see here. But then because for 1990 and 2010, we were still using Landsat 5, we just transferred that model to those years and produced new mine estimates for those years. What's important to note here is that we did collect validation data for 1990 and 2000 and tested our transferring to see if it actually worked well. And it did work well in many cases, which was great because this saves us a lot of time and a lot of effort collecting new training data every year. We also, for onwards, we will use this new method, and we're planning on, or I know Environment Canada was planning on continuing to use this transfer method using benchmark years as well. This is an example just showing a single mine in British Columbia, 1990, 2000, 2010, and 2018. You can see our classification accuracy here, it's quite high. Again, this is based on the validation data that we collected. As with all classifications, I take accuracy with a grain of salt. However, the visual inspection of this is quite promising. And you'll note, I'll talk about this in a second, but there were issues with differentiating rock outcrops or the tops of mountains and differentiating mines. And I'll talk about a little bit why that came about and how we solved that problem. So Sabrina specifically asked me to talk about SAR in Google Earth Engine. And SAR actually helped this problem significantly in a couple different ways. So the first is in differentiating tailings ponds from in our classification. And one of the problems is that with optical imagery, these tailings ponds, the materials are highly variable, the local geology is highly variable, the depth of water is really variable, and they look very different in different cases. And so optical imagery, you get this really wide spectrum of different types of responses from tailings ponds. However, with SAR, water has a specular response. And so you can see what a specular response is here. And it basically means that water looks very different from all other things, and it doesn't matter what the contents of that water were. It doesn't matter what the conditions were. So adding Sentinel-1 VV enabled us to really, really map well the tailings ponds. And then also, SAR is very sensitive to roughness of surfaces. And so we had problems with differentiating mines from urban areas, and also, as I mentioned, bedrock from mines tailings piles. And SAR really helped us improve our classification and enabled us to differentiate these objects in our classification, mainly just because there's different textures, there's different roughnesses, and we had big problems before. Adding SAR really solved that and improved our accuracy. So you would think that because of this, SAR would be very, very important to our classification, and that is very true. So we looked at variable importance using random forest, and DEM came out as the most important, and partly that is due to, I believe, the relationship I talked about with mountaintops being exposed bedrock and them being confused with mines. So elevation allowed us to differentiate that in a lot of cases. But Sentinel-1 VV is our fourth most important parameter, and that really shows how important it is because we had hundreds of parameters to test in this case. So you can read this paper. There's lots more details in here. This was written by Mayor Fuentes, who is a student in my group at Environment Canada. And if anybody needs this PDF, I can send it if you want to email me. The next project I'm going to talk about is carbon cycling in peatlands. And I do a lot of peatland mapping from a lot of different aspects. I'm going to try to talk only about a few specific areas today, but peatlands are wetlands and they are a net carbon sink. So accumulation is greater than they store carbon, which is great for global warming and reducing our emissions numbers. But what we don't know is what's going to happen in the future when we have increased warming and increased or changed precipitation. And these relationships are going to be different in the different types of peatlands. So I have pictures of 3 different types of peatlands here. You can see they're highly variable. But we also don't know how those are going to react, if they're going to react differently or not in the future. And so we really need to map where these different peatland classes are. We don't have a good map of that for Canada. But then we also need to look at the carbon relationships in these different sites. So I'm going to talk about a couple different areas where we can use big data, Google Earth Engine, and other examples to do that. So the Canadian Forest Service maps forested peatlands across Canada for lots of different reasons, and one of them is for carbon emission mapping. We want to map different peatlands throughout Canada, but the big challenge is using optical imagery, and C-band SAR does not allow us to differentiate tree peatlands from upland forest, or it's very inconsistent whether we can do that or not, depending on the type of forest and the type of forested peatland that we have. So C-band SAR is a relatively short wavelength, so 6 centimeters. ALO's PAL-SAR is a longer wavelength, it's L-band, which means it penetrates vegetation. So that allows us to really understand the differences in wetness between and within the peatlands. And instead of using the ALOS data set that's been added to Earth Engine, we decided to use a very specially designed one by a research scientist at Canadian Forest Service, Andre Beaudoin, and he's developed several different indices, the Radar Forest Degradation Index with ALOS, and now we're looking at a wetness index for peatlands. So we did do this in Google Earth Engine, but we didn't use the stock ALOS data set. And what I wanted to say there was that we are developing a very fine detailed peatland map for all of Canada. It's not done yet, but then this will be used in all sorts of different ways, including carbon emissions estimates. I also wanted to touch on the C-band SAR issue a little bit more. And what I found is that C-band SAR amplitude, so the information you get in Earth Engine from the GRD product that's available, does not differentiate our peatland classes. And in this case here, I'm showing an example where we have a peatland that's in an agricultural area that's surrounded by upland forest. And this graph here at the bottom, you can see is amplitude over time. And there's no point in the year where those classes can be separated well on any given day or even over time. There's so much overlap between those that we can't use Sentinel-1 alone to map a peatland, and adding Landsat doesn't really help in, or Sentinel-2 doesn't really help in differentiating forest from peatland. However, there is another option, which is to use single look complex data, which still contains phase information. So in this case, we're talking about SAR interferometry and looking at pairs of images and essentially looking at the change that has occurred over time. So coherence is sort of like the cross-correlation coefficient between the two images. It says how similar they are, or it shows you what changes occurred. And so if you've had vegetation growing between the two images, let's say you have an image on May 1st and May 12th, and vegetation has grown significantly in that time, then you'll have really low coherence. But if you're looking at an area where very little changes occurred, like in a parking lot or in a peatland where there's very little vascular vegetation, you will have a big, a high coherence and really similar results. So I looked at using Sentinel-1 coherence time series, and you can see that on most dates, the classes are very separable, and over time, there's a huge separability between the upland classes and the peatland classes as well. So this is published in remote sensing. This is an example of the classification results. And you can read this paper on MDPI remote sensing. It's open access. If you have any questions about it, let me know. Or if you need me to send it, I can. But what I showed here was that coherence, specifically Sentinel-1 time series coherence, was better for classification of peatlands than using amplitude information alone. And I compared Sentinel-1 and RadarSat, but we can't use RadarSat outside of the Canadian government, basically. The last thing I wanted to talk about is moving away from mapping, moving away from classification, and looking at estimating carbon accumulation or understanding the carbon cycle in peatlands. And so we don't know what's going to happen to peatlands under climate change scenarios. don't know if there's going to be increased decomposition or increased whether we're going to have more storage of carbon or we're going to actually be expelling carbon into the atmosphere. And one way to look at this is with peat cores, because they contain a history of what has happened in a peatland over time. So you can see we have high bulk density peat here and obviously looser peat up the top where it's younger. And we can measure the rate of carbon accumulation in these peat cores. So a master's student from University of Quebec, Montreal, Geneviève Corneau, is doing this. We worked on this in Environment Canada together. I'm supervising her master's thesis, and she's looking at whether greening in the Arctic is related to carbon accumulation. So there's been papers where greening in the Arctic has been dominated, but we haven't really focused on peatlands. And peatlands are different because they don't have this vascular vegetation a lot of the time. Sometimes they do, sometimes they don't. And so Jen is looking at different permafrost conditions and different peatland types and trying to determine if there's a trend in greening and whether that trend matches the rate of carbon accumulation. So her thesis is almost complete. I can give you a little snapshot. Advanced results are at some sites we do have a relationship between NDVI and carbon accumulation, and some we don't. So look forward to that paper coming out soon. Just at the end, I wanted to talk about some of the challenges that we have in estimating emissions and how they fit in with Google Earth Engine and other cloud sort of programs. Emissions have to be estimated for an entire country every year. And so for Canada, we have a gigantic country. We definitely need to use some sort of big data approach. And we also need to go back and update our methods when we've changed. So if remote sensing wasn't used before, then we need to add it. We need to go back and reproduce all of our numbers from 1990. So obviously that is an excellent example of using Google Earth Engine. I talked a lot about area change, but I wanted to highlight at the end that the area change is only half the equation. We still need to know what emissions estimates are going to be in that area change. And so in order to do that, we really need to get out and physically measure things. We can't do this with Google Earth Engine alone. We need to have data about, for example, peat cores or biomass growth or other sorts of biophysical conditions. And so we need to actually get out there and start collecting data. And there's very little or no trustworthy ground reference data available for validation of results. And that's also for biophysical conditions, but also for just mapping classes. We don't have that data available for such a large country. And so we need to, again, get out there and map these locations in order to use the data that we have in Google Earth Engine to our best advantage. So finally, I just wanted to thank people that I worked with at Environment Canada, Canadian Forest Service, and UQAM. If you have any questions, my email is at the bottom. I'm on Twitter. I'm not super active on Twitter, but feel free to ping me if you have questions. And thanks for listening, everybody.
Thank you, Koreen. That was a really great presentation there. So now I'm turning over the screen to our Slido, which is the platform that we're going to be using for the question and answer. So if you just head on down to slido.com and type in the event code, which is #EEVM, it will take you to this page. So I'm just going to leave this up here for a few more moments while people head on to the Q&A site. Right. So at any point, feel free to post the question and it will appear here on the website. So I first like to go ahead and start thanking Koreen again for the great presentation she gave. And I would like to open the floor up to any questions. And in the meantime, while the questions are coming in, I have a question for Koreen. So you talked about right at the end when you were summarizing the usefulness of like big data platforms like Earth Engine for the greenhouse gas emissions inventories. You also mentioned the lack of validation and training data. I've seen certain efforts such as by Radiant Foundation to start collecting large data sets that can be used for validation of remote sensing products. And I've also recently learned about, during Year for Good this year, the adventurous scientists who nonprofit that's encouraging people who are backpackers or trekkers, mountain bikers to go out and collect training data for scientific research. How do you see some of those efforts playing into, like, can citizen science or large foundations like play into gathering this training data for the kind of work that you're doing?
Thanks, Sabrina. Yeah, absolutely. I think that that's great for a lot of mapping, as in classification type of work. Sometimes on the biophysical side, though, it's more difficult because we need measurements of things like water table levels continuously over time, or even eddy covariance towers set up and things like that. And so those sorts of things, they are harder for citizen science to map, but definitely we could be looking more towards that. Another problem too on the classification side is just that a lot of times the classes that specific projects require are not straightforward. So for example, when we were working with a land use classification problem, looking at urban expansion and development, and we had maps over the years showing different types of classes, but we needed finer detail in some cases, or we needed to aggregate data in other cases. And so sometimes it can just be a data management issue, but sometimes there's just not the information there with that sort of data. So absolutely, like, we were trying to find data from as many possible places as we could. And I think that citizen science could be a great addition to a lot of these things, but it's kind of hard sometimes because they're not always perfect for your method or your purpose, right?
Right. Yeah, absolutely. So we now have the first question in from one of the viewers, and the question is, you said the Canadian Forest Service mapped forested peatlands. How did they do it, and how do their results compare to yours using Earth Engine?
Yeah, it's a great question. So I actually work really closely with the people at the Canadian Forest Service who map peatlands, and we're working together to map them. Dan Thompson did some mapping with peatlands in 2016, and he used forest inventory data. So he didn't actually use remote sensing. And now we're taking that effort that he did and scaling it up and doing it in Google Earth Engine. So I can't really compare the results because I've been involved in the projects, but the results are good so far. Again, we have the problem where we have lots and lots of area and highly variable situations across the country. So we do need lots and lots of training data. And that's one of the advantages of working with a group like Canadian Forest Service, is that they do have lots of data that they've measured across the country. So hopefully the results will be excellent and you'll be able to see that published soon, but we're not quite done yet.
Awesome. Thanks for sharing that. So I have a suspicion that a number of people who are watching this session are curious about SAR data. There are plenty of people who have had experience using remote sensing optical data, but then SAR is just becoming more and more visible, and there are so many useful scenarios where incorporating SAR data can really improve the kinds of work that people are doing, like you mentioned, for measuring roughness, or getting that being able to distinguish water from other types of land classes much better. So my question would be, how would you recommend, are there any good resources out there that someone who has mainly used optical remote sensing data and wants to learn more about SAR data, how can they get started? Do you have any tips?
That's a great question. So I can tell you how I got started. This was more than 10 years ago, or about 10 years ago. I had only ever worked with, I was very focused on LiDAR data actually when I first started doing remote sensing. I'd done some optical mapping as well, but I got hired at the Canadian Centre for Remote Sensing, and I was basically going to assist one of the research scientists there, and he was a SAR expert. So his name's Rita Tuzzi. And he basically gave me, he and his another person who worked for him, Gabrielle Gosselin, they gave me a crash course in SAR and said, okay, go for it. And the thing for me was that there's so much math and physics involved in SAR textbooks, is that I found it really, really difficult when I first started because my math background wasn't strong enough. And so my method of learning SAR was basically getting advice from them, but self-taught in the understanding how equations work. So for me, I attacked it as a data science problem, essentially, where I used measurements to understand what was going on. And over time, I learned, okay, when a measurement looks like this and the SAR looks like that, then I know that this certain thing is happening. I know it's getting wetter, or I know it's, very treed here. And so it was a very trial and error sort of introduction. And I wish that I had had a more formal training. And then over the years, I've taken more courses and gotten more comfortable with it. But there's a very good resource on the CCRS website, the Canada Centre for Remote Sensing. They have a good tutorial there. For me, it was combing through textbooks. I have a big fat textbook manual that I consult every once in a while, and it's not the newest resource in the world. I've seen recently that the Alaska Satellite Facility, I think, has been putting up some really interesting material. And so my recommendation to people who want to learn about SAR is try to find a mentor who has lots of experience, because it can be really overwhelming with all of the different information and people coming from all different facets of science, physicists and mathematicians and remote sensing people and people with all kinds of different backgrounds presenting things in different ways. ESA actually also has lots of good tutorials. And play with data and see what, real world measurements are showing you about what's happening in these different pixels and why you see different responses in SAR. And I would say start out with really simple problems. Like the simplest problem is probably water versus land differentiation, but even that's not super straightforward with SAR. So I would say don't be scared. I definitely didn't know any of the math background when I started, and still am not super savvy with it, but really understand the physical geography principles and try to understand the basic physics. And if you put those together, then you'll be able to understand what's going on.
That's really good advice. And I really like what you shared about looking for a mentor who is experienced in this, and then also playing with data and asking why data is showing certain results. So that's definitely great advice. I don't see any more questions. Are there any more questions from the people who are here on Zoom? You can also type in your questions in the chat if that will be easier for you.
Koreen, I had a question about, so the way you would get greenhouse gas inventories from satellites, there is the issue of scale, right? Like the data you're using for training is probably more localized. And for some regions like, marshland, or maybe if you're in an urban area, there could be very localized sources of emissions. How do you account for that?
That's a really good question. So that in my opinion, there's a two-pronged approach to that. So first of all, using higher resolution remote sensing data can give you more precise estimates of what's going on in these different regions, but that's difficult to do nationally, especially for Canada. But on the other side, on the emissions factor side of things, so knowing that in marshes, they behave this way, they act this way, and in certain types of marshes will have this condition, so this type of emissions estimate this type of emission might occur, is basically how it's done right now. So it's not a precise number of, yes, this specific marsh emitted, 2 units of carbon per year. But it is a more general idea. And the same thing for like sinks as well, with peatlands or with other wetlands where you're storing carbon. We don't really know necessarily how deep a peatland is, but we make estimates about it. So we get the area from remote sensing, and then most of the time the emissions factor is some sort of approximation that's approved by the IPCC. So the IPCC has country-specific emissions factors that are approved basically by them to use. So we don't all just go make up our emissions factors, but you can improve emissions factors as well. So we could go study a certain peatland or a certain number of peatlands and say, oh, well, actually, we see that the methane emission is actually higher than what we're reporting in the IPCC guidelines. So therefore, we'll make an improvement to that method. So that's also a possibility as well.
Mm-hmm. Thank you. That makes sense. I was wondering because you mentioned like eddy covariance towers, and I used to work on eddy covariance towers like many years back. And one of the issues has always been that for sensible and latent heat fluxes like moisture and heat fluxes, it's an okay amount of accuracy, but when you start looking at carbon flux, the accuracy can be like as low as, you can have like an uncertainty band that is like half the value, the actual magnitude. So even with observations, there are those issues, plus representativeness of the towers themselves. It
Yeah,
has been
absolutely.
of course an ongoing problem, I guess, with like trying to constrain the carbon budget as a whole.
Absolutely, yeah. And the footprints like of the instruments that we're using are all different, right? So absolutely. It's an estimation, I would say, not a precise number.
Thank you, Koreen. So are there any more questions from the audience? If not, we would really like to thank Koreen again for taking the time to prepare this presentation and for being our guest speaker this week. She shared her Twitter. She's at GeoKoreen. So if you'd like to follow her on Twitter, you can go ahead and do that as well. So thank you so much again, Koreen.
Thanks, Sabrina. Thanks for having me.
Yeah. So right now we're going to head into the troubleshooting tips and tricks session. So please, if you have anything that you're working on, feel free, and you're stuck and you want some help with it, or you're looking for some data sets or some tips for how to do something, please feel free to go to the slido.com website and type in your question there. And if you're in the Zoom as well, feel free to, you can also type it in chat and I will read out your question. So do we have any pressing areas that we can support you on? People who are here? Right, it looks like a pretty quiet group of people. But anyway, if you like, for those in the Zoom, please feel free to also introduce yourself and add your Twitter contact so that we can all stay in touch after the session. I see another question that just popped up for Koreen. How much of SAR processing can be done in Google Earth Engine?
That's a good question. So the SAR data that's available, the Sentinel-1 data that's available in Earth Engine is the GRD product data. Anything that can be done with GRD products can be done in Earth Engine. So you'll see there's lots of examples with OTSU for doing water and land classification or differentiation. Any sort of mathematical function that you want to build, you can do that in Earth Engine. But anything that that requires the phase information, which is what I was talking about with the coherence information, and also if there's no polarimetric component or there's only dual pole SAR available with Sentinel-1, so there's no polarimetry or polarimetric analysis that can be done. But basically anything that you can do with dual pole GRD data, you can do in Earth Engine.
Thanks, Koreen. That was a great answer. So do we have another question here? Has anyone set up an Earth Engine web app based on the JavaScript API that can be automatically updated? So I think we need a bit more clarification about this question, but basically there is a way to make sure that your app code is always updated. When you are creating the app itself in the code editor, you can choose whether or not you want the app to be based on what is currently in your repository on the screen, the existing code that's on the screen in the code editor, or you can link it to a specific path in the code editor so that every time you update that script, your app will also be automatically updated. Is this what you're asking, or are you asking like, how can you write a script such that, for example, if it's displaying the most recent Sentinel-2 image, that it will always be the most recent Sentinel-2 image? If you'd like to follow up with another question, that will be helpful. And yeah, are there any other questions that we can help you with? All right, looks like all the questions have been answered. So I'm going to go ahead now and go back to the presentation here and exit full screen mode. So once again, for next session, we're really excited to have Cesar Ibar joining us, who will be talking about RG. For those of you who use R, this is a great way to start using Earth Engine as well in your R code. So don't miss that session. It's on the 25th of November at the same time. And then on the 9th of December, we have Abina Sariansa, who will be talking about monitoring aerosol concentrations in the Sahara Desert using Google Earth Engine. So please feel free to mark that date as well, the 9th of December on your calendar, and we will send out more information for those who are registered for the talk. So I'd like to say again, a big thank you to Koreen for her presentation. Thanks to everyone who's here and joining us. We'll see you all next time. Have a great rest of the week.